All right, good morning, everyone. Thank you for attending today's webinar on the third of our three-part series, Heat Pumps. This webinar is recorded and the recording is posted to the Code Adoption Toolkit. I believe that the previous ones have been posted, but I will double check. I know I've gotten a couple emails from you guys to see where that is exactly. So I will look into that. If there are any issues with audio, please feel free to write me in the chat. My name is Erica DeLello. I'm a senior project manager for Noresco. And we have Ken here who created the training materials. And this series is sponsored by the Colorado Energy Office. So Ken and I have been doing a couple of these trainings. As I mentioned, this is the last of this series in particular on installation as it relates to heat pumps, but there's more. We still have more webinars coming down the pipeline for our normal Wednesday webinar series that occurs at 12 p.m. We've got one next week on blower door testing, and the following week is radon testing. So definitely reach out. Or I will post in the chat actually the link to register for those as well. But we also offer a variety of other types of training, including role-based, where it basically looks through the energy code through the eyes of the user and tailors the training to your background specifically. So whether you're an engineer, building official, an inspector, plan reviewer, you name it, we have a training for you guys. And then we also do tailored group trainings. And then this is that lovely Code Adoption Toolkit that I mentioned. It's got a whole bunch of different resources on it, but my favorite resource that we offer is the Colorado Codes Helpline. You can submit a question on any of the I-codes and get subject matter expert gets back to you in just a couple days' time. Okay, let me just see if I hit all the points. And I did launch a survey just now. If you guys could take a minute to fill that out, that would be wonderful. And then there will be a post-training survey. If you guys could fill that out, it takes about a minute, and it helps us to improve on these webinars. And then I saw a question in the chat. The certificates are sent out at the end of the month, Sebastian. So that will expect that in your inbox in the next week or so. Okay. All right. And today's presenter is Ken Carlson. So Ken, I'm going to go ahead and pass it over to you.
Sure. Thanks, Erica. Just give me a minute to get situated. All right. So you should see the presentation.
Yep, looks good.
All right, good. Thanks, Erica. All right. So as Erica mentioned, this is session 3 of 3 on heat pumps. Today, we're going to be talking about a little bit more about heat pump installation. Hold on a sec. There we go. Our agenda. So we'll talk about installation considerations, requirements, best practices. We'll go over some of the tools required for installation service. Some tips and things to note about charging systems, evacuating systems, pressure testing. We'll go over ACCA 5QI standard overview. As part of this, we won't dive deep into it, but at least give a little bit of what it is and what it means. So welcome everybody. The session will cover the essential aspects of heat pump installation, including required tools and ACCA Standard 5 quality installation requirements. The objective, gain an understanding of heat pump installation considerations and best practices. There's a recap of the last couple sessions. Session 1, we talked about what a heat pump was, how it works, talked about different types of heat pumps, ducted versus ductless, air sourced heat pumps, water sourced heat pumps, air to water heat pumps, talked about dual fuel systems, some of the benefits, and then we did talk about some of the cost comparisons of operations between gas fired and different fuel options versus heat pump and pure electric. In session two, we discussed about when to install a heat pump and things to consider for new construction and retrofits. The applications of the different types of heat pumps. We talked about when to keep existing systems and add a heat pump, how to mesh a heat pump with existing systems, how to utilize dual fuel system, and whether or not to use existing ductwork when you can't use ductwork, what the infrastructure of the house looks like, how to select the type of system you're going to use, how to assess the environment of where it's going. We talked about load calculations with manual J and how to establish what size heat pump or what size equipment you actually need. And then we discussed a little bit about the manual S, or how to actually appropriately choose the size of the equipment based on the dwelling needs and the manual J load calculation that was done. So that's just a recap of the last two sessions. In this one, we're going to talk mainly about the installation process, things to consider, things to note, best practices, and such. So getting into this presentation, ACCA 5. ACC 5 is the HVAC quality installation specification. If anybody's not sure, doesn't know what ACCA is, Air Conditioning Contractors of America. They set out different standards, in the air conditioning realm, including manual J's, manual S's, manual D's can all be found through the ACCA. So ACCA standard 5 has to do with the quality installation. It's basically a quality installation specification. It's the industry standard that specifies appropriate installation methods for residential and commercial HVAC equipment. Heat pumps are included in that specification. There could be, in certain circumstances, requirements for rebates or even code compliance to adhere to ACCA 5 to make sure that the equipment is actually designed, installed, and commissioned properly, so that they know that the rebates and the energy savings would actually be received. So if anybody's curious about what's actually in ACCA 5 QI, this is the table of contents. All right, it goes into some of the stuff that we talked about: heat load, heat gains, equipment capacity selection. They talk about heat pumps, geothermal systems, matching systems, making sure that the indoor and outdoor units are actually a match set, and that you can actually specify what the actual operating parameters are, including efficiency. Does go through installation aspects, refrigerant charging, electrical requirements. There's several different things in here. It even goes down into balancing and duct leakage, which we didn't really talk about too much. We'll touch base on that later in this session. So just a little bit of, it's easily you can search this. You can even download this online. It's not hard to find. It's good to read through for anybody so that you kind of understand like what the actual requirements are, and see whether or not you're doing that in your installation. What you could actually potentially be doing better or should include, moving forward. So getting into installation, pre-installation setups, you've done your site assessment, you figured out, where you're putting your indoor unit, you figured out where you're putting your outdoor unit. You verified that you've got enough electrical capacity. You've decided on the type of system you're using, whether it's ducted or ductless or whatever it might be. You've done your size selection. You've selected the type of heat pump you're putting in, or system for that matter. Doesn't necessarily have to be a heat pump. You've done your manual J. You've ensured that your indoor and outdoor units match, and you have an AHRI rating on it. You've got your manufacturer submittals, so you know all your sizes, capacities, and such. You've obtained your permits, you've ordered your materials, and now you're going to do your installation. So we're going to jump right in. So just taking a wall unit, for example, on a heat pump on like a mini split, just because it's one of the most common installations that are out there. Many different options, very versatile. You'll secure you're setting your indoor unit. You got to secure a mounting bracket. You got to drill your hole to get your refrigerant lines and drain and power from that unit to another place, typically outside. You got to connect your refrigerant lines, condensate drain, and then you'll get to mount your indoor unit. So typically the indoor units, they all have a bracket, a mounting bracket. On that mounting bracket, there's actually indications as to how to line up your center line for your hole. Typically you'll utilize one hole, in that that penetration, in that hole, you'll go from your interior wall to the exterior wall, and all your refrigerant lines, your drain, your power and communication lines all go through that same penetration. This photo is a little overkill, but one thing to note when you are drilling through a wall, whatever the material may be, is to keep a pitch going down. That is for the actual drain line itself. We want to make sure that the condensate, can go downhill and actually leaves the pan and to the next point. This is just kind of what you would see when installing, a wall-mounted unit. This person's already connected their drain lines. They've already connected their power and communication lines, and now they're pushing the whole unit through the wall. Once everything is through, you'll clip it on the bracket, snap it in place, and then you'll make your refrigeration connections outside the wall. It's typically on the exterior. It can be on an interior, it could be an interior wall. It could be even in between the wall or in the wall cavity. But typically, for an existing installation, you're on the exterior. Conversation on drainage. All right. Important, right? Make sure the drain lines are always sloped downward, industry standard, 1/4 inch per foot. Avoid long horizontal runs when possible, pretty straightforward. Exterior walls with drain lines to a location away from the foundation or walkways. Don't discharge directly on a building or on a roof. If a case came across where you did have to, put a condensate line onto the roof, which is not really recommended, make sure you have a protector underneath it. Otherwise, that constant dripping from the condensate will wear away the roof. When installing units, and this really has nothing to do with, mini splits or anything like that. When installing units in attics, basements, crawl spaces, make sure you put a secondary drain pan underneath that air handling unit or evaporator to catch any kind of overflow or spills that may happen. At some point in time throughout the life of that equipment, it is very likely that that drain line is going to clog at some point. You need to have something auxiliary pan to catch that condensate, or you could end up with a mess. In that auxiliary pan, that secondary pan, should be a float switch or water detector, something for you to understand or indicate that you're in an overflow condition. Something needs to be done. A lot of times the float switch is there. It's hardwired into the unit. It'll shut the entire system down, or at least the air conditioning down. You have a problem. It prompts somebody to actually go take a look and address the situation. Thermostat installations. Install thermostats near central return air locations, pretty common. Make sure they're in common areas. You put a thermostat in a room, shut the room door. It's going that shut door, that thermostat's going to be influenced by the air in that room alone and not the rest of the house. Avoid exterior walls or locations influenced by sunlight or temperature. Seems straightforward, but take a look around before you put a thermostat on a wall. Make sure you're not in the hallway at the upper floor with a big window that's going to allow light to shine on it for 3 hours out of the day. Definitely try to avoid the exterior walls. The exterior wall will influence the temperature that thermostat actually sees or senses. So ductwork considerations. You've done your ductwork sizing per the manual D. All right, you got all your sizes. You got your layout. You install your ductwork. I can't stress enough ductwork sealing. All right, and when I mean sealing, I mean like sealing up joints. All right, most ductwork, particularly in residential applications, it's slip and drive. It's a real loose connection, or you're cutting in, round. You're cutting around ducts for flex or branches. Depending on which type of collar you're using, it could seal well, and it could be a real loose connection that allows a lot of air to escape. At all your connections, utilize either a mastic or tape. Tape works, metal tape at all your joint connections to try to eliminate as much leakage as possible. It's only going to hurt you. You want to get all the air, not just some of it, all the air to the rooms and not to attics, crawl spaces, basements, or anywhere else the ductwork might be. Make sure your ductwork's supported. Make sure everything's insulated. Particularly if you're in a humid climate, insulation is about preventing condensation. It's more than just preventing condensation. It's making sure that whatever conditioning you're doing, whether it's cooling or heating, that conditioned air is making it to the space at the same temperature that left the unit at. Anything uninsulated, you're going to be losing temperature or gaining temperature, in the environment that the ductwork is in. A couple things to know about ductwork, right? Typically, the insulation, ductwork insulation, right? It needs to have an R8 value, right? That's required by IECC. It's also referenced in ACCA. You typically use FSK. It's foil scrimcraft. It's what they call the fiberglass insulation that you see here on the bottom. That has an R8 value. A lot of people these days are using bubble wrap. All right, bubble wrap doesn't actually have an R8 value, depending on whether you're using the thin or the double. Even double bubble, as the industry a lot of times call it, it's a thicker bubble wrap. Even that doesn't have an R8 value, to my understanding. I think it's an R6. But regardless, in order to obtain that R8 value, you need to actually have spacers. You need to put an air gap, in between the bubble wrap and the ductwork. You do this with taking basically another small section of bubble wrap, you tape it to the ductwork, and then you wrap around that. It creates an air gap in between here. Something to note: depending on where you're at, it could be enforced by local code as well. And your vapor barrier must be maintained. What I mean by the vapor barrier, basically all this insulation that you're wrapping in this ductwork needs to be sealed. All your joints need to be taped. When you get to a unit or you get to a transition or whatever it might be, the insulation needs to be taped to that unit or transition to maintain that air, right? Typically it's humid air, right? That would go in here and potentially cause condensation in here. So hence the name vapor barrier. So again, just make sure everything is sealed and it's tight and taped. So outdoor unit installation. All right, you've chosen your suitable location, right, during your assessment. You prepare the base. If it's going on the ground. If you're in a cold climate with a lot of snow, chances are your base is not going on the ground. It's going up on a stand or it's going up along the wall. Make sure your clearances are here too. Make sure your unit is secured, but onto whatever you're putting it on. Different types of bases, ground stands, wall mounts, ground pads, and roof mounts. Roof mounts probably the least favorable for anybody, but sometimes you have no choice. If you're in a cold climate where you have, even any kind of amount of snow, you're probably not putting your heat pump on the ground, or you're going to be burying it in snow. So, the outdoor wall mount is probably the most common, or even a ground stand will suffice with enough height and clearance for local snow height. That, depending on the area, and you have to go to your local code officials to figure out what their actual the snow line is, right? As far as what you designed for, depending on where you're at, could be a foot, could be 2 feet, 3 feet. Understand and know what it's supposed to be. Avoid sides of the houses that are going to get a snow drift. Just a piece of advice. So make sure you got your proper clearances from your structure, snow depth. Take into account the defrost water runoff. So what do I mean by that? So we talked in earlier sessions about these units needing to go into defrost. Frost will build up on these coils in heating mode in the winter. They go into defrost cycle. It defrosts all that frost that's built up on the exterior unit and melts it, and it drains out the bottom. These are a couple photos from a heat pump in Minnesota. You can see how much condensate, it's not even condensate, it's just defrost water, has been dripping out of this unit day after day, and it builds up. All right. And make sure your height is enough where you're going to limit a situation such as this. You can actually drain these to a different position. They do make little fittings. You can put in a drain line. If you did something like that, you would need to put heat trace on that drain line to make sure that water will actually drain out the drain and to another location. Avoid placing these units near walkways. Shown in the picture on the left, and I can't tell you if that's a walkway or patio or whatever it might be, but that defrost water that's been melted is piling up, and now it's making its way over to a walkway. You're going to end up with a slipping hazard. Don't mount this over a walkway in a cold climate condition. A lot of times, if this was actually mounted on the wall, you could put something porous below it, rock or such, something that'll allow water to either build up on that rock or eventually melt and go into the ground as opposed to on the concrete or blacktop surface. So same goes for an air to water heat pump. These heat pumps are typically heavier. Probably not going to be mounted on the wall. I have seen them mounted on the wall, but there's been special precautions have been made, and things have been modified and changed to support the extra weight. Structurally have been changed to support the extra weight on the wall. Typically, you'll see these on a stand. Just make sure the stand is high enough. Make sure it's on a platform strong enough to support the weight, and it's not going to shift. Concrete pad, ideally. Make sure your lines are insulated. There'll be a glycol solution in here anyway, but you don't want to lose any of that heat, to the outside. You spent, energy actually generating heat. You want to make sure that heat goes to the inside of the house, not outside. We talked a little bit about air to water heat pump installations. These are pretty intricate systems. There's a lot more to these systems than a standard boiler system. You need to make sure that you have your interior space for your buffer tank. You need to make sure you have enough space for your extra pumps, piping, valving, expansion tanks, glycol feeds, whatever you might have for these systems. Biggest thing being the buffer tank, as it's quite sizable. Generally, buffer tanks are in the range of 40 to 120 gallons, depending on the size. There's some different industry, terms out there, 20 gallons a ton. Is a number that's thrown around a lot. The manufacturer will oftentimes help you calculate the buffer tank size that you need to make sure that it's sized appropriately. Depending on the heating capacity, temperature of the system, what you're actually serving in the system, it will change how big that tank needs to be. So make sure it's sized appropriately. Those don't go by rules of thumbs. We talked about before, the buffer tank is there to manage short cycling and maintain consistent performance. We talked about how the heat pumps need to go into defrost modes. They don't respond to temperature changes, immediately. That buffer tank is there to mitigate some of that. So it's a requirement. As far as water source heat pumps, that might be used for air distribution, right? So a geothermal system, essentially. You have your typical ductwork connections. You got your typical electrical connections, much the same as an air handling unit. Difference is that this is a package deal, all right? Your compressor, your evaporator condenser or coils, right? With the heat pump, it goes both ways. All part of this package. Your water connection from your geothermal system will get connected to here. There's the heat exchanger in this bottom cabinet, and that's going to be your transfer medium for in cooling and heating, right? So again, it's all this would be self-contained for the most part. You would be in charge when installing, in charge of connecting your ductwork, your electrical, and your water lines. They come pre-charged. It's all ready to go. Just needs to be started up once everything's connected. Just a little bit of information on geothermal piping. When installing these systems, you'll have to have a glycol solution. All right, temperature going back to the ground in heating mode could be below 32 degrees. You'll need a pump. All right. Typically these are manifolded together. If they're vertical wells, oftentimes they are piped in what they call a reverse return. So what that means is that on your supply line, right, your supply going into the building, what would be considered your first takeoff, right, is the last takeoff on your return. And what that does is that equalizes the length of pipe on each one of these branches so that the flow is the same. So if you didn't do it in a reverse return, you'd have to actually install like a balancing valve or something, and then you would have to adjust and balance all these different lines to make sure that your flows are equal between each of them. So oftentimes you'll hear people say reverse return. This is essentially what they mean, right? Your first on one side is your last on the other side. Distances between, try to equalize everything like that so that all your lines are essentially have the same amount of piping and therefore the same pressure drop. Any questions up until this point? I'm just going to pause for a second before we go into a little bit more into the installation of split systems and refrigerant charging and vacuums and pressure testing.
Not seeing any questions come through. Folks you can submit questions in the Q&A or in the chat, or even raise your hand.
That's fine. I mean, that a lot of that was just for information.
Okay.
We're gonna go into a little bit more of what typical installations of the most common systems that will be seen out there. So most commonly, you're going to see air-to-air heat pumps. It's the most common system out there. That's what we kind of want to get into as far as, best practices, things that need to be done, tools that you will be required to actually do an installation like that. Whether you are a contractor or if you're a homeowner that thinks you want to put one of these in, there's a good amount of information you need. There's a good amount of tools that you need and require an initial investment. So you'll need a set of manifold gauges. You'll need a set of manifold gauges for each type of system or each type of refrigerant at the very least that you're working with. I even recommend a different set of manifold gauges from, a standard residential split system and a mini split system. Connection sizes tend to be different, and the oil within those systems is different, right? You do not want to mix and match refrigerants. You do not want to mix and match oil between systems. The cleaner you can keep your internal components on system, the less problems you'll have, the longer it'll last. You'll need a vacuum pump to pull a vacuum. You will need a refrigerant scale to weigh refrigerant as it's put into or out of the system. You need a flaring tool specific for copper pipe, for refrigerant pipe, I should say. You'll need a brazing kit, so in case you need to braze anything. You'll need a micron gauge. You should have a torque wrench set. All right, there's torque values provided for flare fittings. You should have a pipe bender, right, to make bends as opposed to making joints, and you will need nitrogen and a nitrogen regulator. So, a little tidbit on brazing and nitrogen purging. All right. Should you have to braze any joints, and this doesn't just go for heat pumps or split systems, this goes for any refrigeration system. If you're brazing, you should have a nitrogen purge in that pipe that you are brazing. All right. When you braze, the temperatures of the copper become high enough where it starts to react with oxygen. You get oxidation, you get copper oxide. That's the black on piping. If you've ever seen it, anything brazed, you'll see this on the outside. This is also on the inside, unless you purge it with nitrogen. This picture on the right is the difference between not using a nitrogen purge and using a nitrogen purge. All right. When the nitrogen is in there, the copper can't react and create copper oxide. There's no oxygen in the pipe, right? That's the point of using nitrogen. They make special regulators for this that allow just a little bit, the slightest whisper of nitrogen to flow through the piping. If you flow nitrogen through there too fast, you will end up cooling your joint, and then you won't actually get a good joint. You could end up with a cold joint and end up with leaks or porous joint. So just keep that in mind if doing any brazing. Line set considerations. Line sets your refrigerant pipes to connect your indoor and outdoor units that carry refrigerant between the two components. There are maximum lengths for the manufacturer that are allowed on refrigerant lines. They're pretty far. Any standard residential system, you've got enough distance you can get between the indoor and the outdoor unit. You've got minimum lengths. So considerations, right? You want to minimize the lengths within reason. There are minimum lengths too that need to be accounted for in these systems, so just keep that in mind. You want to reduce frictional losses and pressure drops as much as you can. So one of the best ways to do this, use a pipe bender. All right, avoid putting in joints. Use a pipe bender when at all possible. It's one less connection you got to braze. If you can get away without any connections, right? And it's just flare connections, no bend, no brazing joints. You don't have to worry about purging. It saves time. It also reduces pressure drops. It's a much smoother bend as opposed to putting in a fitting with abrupt changes in direction or even obstructions from the fitting connections. Refer to your installation manual for line set sizing. It changes depending on the size of the units. Dealing with multi-zone mini splits, your line set size is dictated by the interior unit that it's going to. So it will change. You could, on a multi-zone system, have 3 different size line sets. It's not uncommon. If your line sets exceed the outdoor unit charge, you will need to add refrigerant. All right. In the manufacturer's posted installation manual, they typically will tell you how much refrigerant you need that needs to be added. When you're dealing with mini splits, they don't want you using subcooling or superheat, which we'll talk about shortly. They want you to weigh it in. All right. So, they'll typically come and we might actually we'll talk about this in a little bit. So connecting refrigerant lines. So most mini split systems utilize flare fittings. They utilize this because it's cleaner. They don't really want you brazing or sweating or doing anything like that. It's a very clean connection. When you get the line set, these fittings, the flare nut will actually come with the unit. Put the flare nut on first. If you flare this first, you'll be cutting it off and you'll be doing it again. But regardless of that, I spoke about a flare tool utilized for line sets, particularly copper. If you use a regular standard flaring tool that you buy from AutoZone or wherever, chances are when you flare this, it's going to split the copper. The flaring tools that you buy for refrigeration systems for line sets, they're concentric. So when they flare that fitting, they actually roll around the edge. And it's much smoother. It prevents cracking. And it gives you the proper angle and proper fitting that you need. It's marked, for the appropriate size so that you get the right size flare. So you've done your flaring, you've made all your connections on your line sets. You need to pressure test your system to make sure you have no leaks. Go to manufacturer's installation manual will tell you what that pressure needs to be. A lot of times it's 1.5 times working pressure. Working pressure varies. Some manufacturers will require actually up to 600 psi for a pressure test. Again, that varies by manufacturer. Use only nitrogen. All right, nitrogen does not fluctuate as much as air, and especially refrigerant. And this way, when you do your pressure test, you leave it under pressure for a prolonged duration, whether it's a couple hours or a day, depending on what you're doing, depending on what the manufacturer recommends. You won't see fluctuations due to temperature and your pressure. You can be confident that your pressure is being maintained. Sometimes people do put trace gas in here, and they'll pressurize with a little bit of refrigerant, just a little bit, and nitrogen, and then actually use a refrigerant detector at all your joints. You can actually soap or bubble check all your joints as well. I would typically do this. I would put my system on their pressure test, make sure everything's stable, make sure the gauge isn't moving at all. I got no major leaks, and then I would go and soap check all the connections. Even sitting here for an hour, sometimes you'd have a leak so minute, so tiny that you won't see it on the gauge, but you will see little tiny bubbles form. It'll give you the chance to reset that connection, particularly if it's a flare connection. And then redo the test. All right. So once you've done your pressure test, you've confirmed that you've got no leaks, you need to evacuate your system. So the evacuation of the system utilizes a vacuum pump. It pulls all non-condensables, all moisture out of those line sets. So on your outdoor unit, and this goes for an air conditioning unit, heat pump, whatever it may be, the units all come pre-charged. These are valves right here with these hexagonal nuts right here. So they come closed. On the unit side is all your refrigerant. On this side is your connections where your line sets are. When you pull a vacuum, these valves are closed. You're pulling a vacuum only on the line set and the interior unit, or the unit coil, I should say. You need to get all the non-condensables out. They'll react and cause problems inside the system, or take up space and reduce your capacity. So regardless, we need to pull a vacuum, get everything, all oxygen, all air, all moisture out of these lines, out of the indoor unit, so that when we do open these valves, there's nothing but refrigerant in the system. You'll need to pull down below 500 microns. That's typical industry standard. Some manufacturers will require another number to pull down further than 500. You pull your vacuum down, you'll need a micron gauge. Your regular gauges won't show you microns. You pull down your vacuum, you get down to below 500. You shut off the valve. You shut off your valve at the vacuum pump, or if you've got a valve in line like they do over here, you can shut off that valve, and you watch your micron gauge. Oftentimes, your 500 microns will go up once you shut that vacuum pump off. You close the valve, your microns will go up. Manufacturer usually will give you a guideline as to what's acceptable. 15 minutes below 1,000 or 30 minutes below 1,000 microns, they'll consider your system tight, and you're good, and you basically can release your charge at that point. And then you can do your startup from there. While you're pulling your vacuum off, the time you'll start making your power connections. the space on, particularly in the mini split, the space is limited. All right. It's stranded wire. I'd recommend, depending on what your connection terminal is like, oftentimes using fork or ring connectors on these will aid in the quality of the connection. You crimp on a fork connector on your wire, put the fork connector underneath the screw, clamp it down, ensures a nice firm, tight connection that's not going to wiggle loose, and it also ensures that you have a good quality connection. The stranded wires tend to squeeze off to the side, and sometimes you don't have the whole entire wire sitting underneath and making good contact. So refrigerant charging, all right. As we talked about before, equipment comes pre-charged oftentimes. If you're doing service work, you would need to charge it. If you've got extra line set, you will need to add additional charge. You will need a scale as shown here, set of gauges, and you also need something to measure temperature, whether it's a thermistor or a thermocouple, but something to measure the temperature of your discharge and your suction lines. Per ACCA 5, and even in the industry for that matter, there's three methods to add refrigerant. You can weigh it in, you can do superheat, and you can do subcooling. All right. Most mini splits, in heat pumps for that matter, they want you to weigh it in. They don't want you doing superheat or subcooling. They want a certain amount of refrigerant charge based on how much piping you have, and based on the outdoor unit. What the unit comes pre-charged with is actually posted on the unit. If you needed to add more refrigerant charge due to more line set being added above whatever it's pre-charged with, you would have to add it. All right. You would have to weigh it in. All right. They don't want you doing superheat and subcooling because of the variations in the system. Those units will maintain their own superheat and subcooling depending on the conditions. So, for example, all right, we talked about heat pumps come pre-charged somewhere between 15 and 25 feet. It's typical, but that does vary, depends on what you're working with. You'll need to determine the length of pipe, right, or the length of line set beyond what was included in the base charge of that unit, right? So, for example, you have 50 feet, you install 50 feet of line set, it comes pre-charged for 25. You need to add refrigerant, right? 50 minus 25, you've got 25 feet of additional line set. You'll go to the manufacturer's installation instructions. They'll tell you exactly how much to add depending on the size of the line set, because that's actually what will dictate how many ounces per foot that you'll add refrigerant for. So a common figure, typically for 3/8, like 3/8 3/4 line set, is 0.6 ounces per foot. 0.6 times 25. You need to weigh in 15 ounces of refrigerant. That'll get you pretty close to your charge. If you talk about a heat pump, they only want you to weigh it in. You'll weigh in your 15 ounces, and that'll be it. You won't do anything else, most likely. So 15 ounces, just so it's 16 ounces a pound, right? So you're an extra 25 feet of line set. All you have to do is add 1 pound of refrigerant. Keep that in mind. If you run a calculation and all of a sudden your calculation tells you got to weigh in 6 pounds of refrigerant, check your calculation again. It's unlikely that you actually need to add 6 pounds in. A pound to 2 pounds is probably typical. Sometimes it's only a few ounces that you have to add. So other methods of setting a charge. All right. System superheat. So what is it? It's the temperature of the refrigerant above that of the saturation temperature at a given pressure. All right. It ensures vapor is going back to the compressor. Right. You can't compress a liquid. You need vapor to compress. The amount of superheat is determined by the indoor dry and wet bulb and the outdoor dry bulb temperature. This would be given by the manufacturer, and it will vary depending on those temperatures. All right. It's typically around 15 degrees. And depending on your outdoor and your indoor conditions, it may be different. ACCA 5 QI says that you must be within plus or minus 3 degrees of OEM specified superheat value. That's a good standard. Even if ACCA 5 doesn't say that, that's a good metric to use. And you want to get as tight as possible. There's variations in how you read your gauge. There's variations in in the gauge itself. There's a level of tolerance of accuracy, even in your equipment. Typically, your charge is actually set with subcooling. Your TXV would be adjusted to reach your superheat requirement. Typically, if you have a fixed orifice system, right? You don't have a TXV, you've got a piston instead, a fixed orifice, you actually would set your charge with superheat and superheat alone. You verify your subcooling as a reference, but you would actually set to superheat. So this is what a pressure temperature chart looks like. We had talked about before. Let's just say you're operating at, you have 410A system. Sorry, I don't have 454B on here, but let's just say you had a 410A system. You're at 130 psi on your suction side. All right, you got to charge and cooling. You're at 130 psi. Your saturation temperature is 45 degrees. All right, so if you were anything warmer than that and you're at 130 psi, you have superheat. 45, let's just say you measured 60 degrees, you'd have 15 degrees of superheat. Going the other direction, if you measured 35 for whatever reason, right, and these were your pressures, and if your pressure was 130 and you were measuring 40, you would be in subcooling, right? So if you're in cooling mode and you're on the discharge side, typically your pressures would be much higher. You'd be much more like, 254, 274, and then you would calculate your subcooling from there. We'll talk about that in a few slides. This is a typical chart of what the manufacturer may provide for you. It gives you an indoor wet bulb temperature. It gives you the wet bulb temperature because the capacity of your coil is a combination of latent load and sensible load. The wet bulb takes this into account. It gives you different ambient conditions for your condensing unit, and the correlation between the two is what your superheat needs to be set to, for that given condition. So if your indoor wet bulb was 64 and your ambient outdoor air was 80, your superheat would be 15, right? So if your indoor conditions were higher, right, but your ambient conditions are still 80 degrees, you could see 18 or 21. So if you're within 3 degrees of that 15, you're probably pretty close. You can try to dial in a little bit. Sometimes it floats around a little bit, needles move. So close to 15, you're good, but get it as close as possible. So what it would actually look like in the field. This is your gauge. You would read all gauge sets, just for anybody that doesn't know. They have the saturation temperatures for different refrigerants on your gauge set. Your gauge set would be appropriate for the refrigerant that you're working on. You would have those saturation temperatures right on the gauge so that you can see at 130 psi, saturation temperature is 45 degrees. If you measure 60 degrees on your suction line, you would have 15 degrees of superheat. For inversely, subcooling, right? So what is subcooling? It's the additional cooling of refrigerant below its saturation temperature, right? We show that pressure temperature relationship chart. At a given pressure, it has a saturation temperature. If you are below that temperature, you are in a liquid state. If you're above that temperature, you're in a vapor state. All right. Again, it's the difference between the saturation temperature and the liquid line temperature. So again, your subcooling value would change with ambient temperature. Refer to the manufacturer's chart. Typically 9 degrees. Don't use that for everything. Again, the manufacturer will give you what it requires at the given ambient condition. Again, per ACCA 5 QI, you should be within plus or minus 3 degrees. Again, back to the gauge. It gives you a pressure. It gives you a saturation temperature. If you were at 230 psi, which equals a saturation temperature of 110 degrees, and you measured 100 degrees on your liquid line going out in cooling mode, right, you would have 10 degrees of subcooling. I don't think this is actually for 410A, so don't pay attention too much to those numbers, but the theory is essentially the same. So that's all I have for refrigerant charging, superheat, and subcooling. Quick note on refrigerant 454B. So 410A was the old refrigerant, 454B is the new refrigerant. As of January 1st, 2025, all systems that you purchase will come with 454B. It's the new replacement for 410A. They're not interchangeable, just so you guys know. Why 454B? It has a global warming potential much less than that of 410A. All right. So remember, anybody that's been around for a while, R22 was the old, refrigerant that was used for years. It had a higher global warming potential than even 410A. 410A came out with the lower global warming potential. Now we are at 454B with an even lower global warming potential. All right, it's a much more environmentally friendly refrigerant. For information, it's actually a blend. It's a blend of R32 and R1234YF. All right. I don't think many people are probably familiar with R32. If anybody has a car that's probably 10 years old or less, if you look underneath your hood, you'll see R1234YF. It's probably what's in your car for your air conditioning system. And probably what's in most common refrigerators these days. So it's a little tidbit of information. So again, just a little synopsis on ACCA 5 quality installation. It's basically a guideline. It's a specification for the installation of HVAC equipment. It's an industry standard that dictates appropriate installation methods for residential and commercial HVAC equipment, inclusive of heat pumps. And again, you'll see reiterating from before, I know I showed the slide already, you could be required to document and adhere to ACCA 5 for either local codes or even to obtain certain rebates. What ACCA 5 does is it lays out a procedure, right, and a method of documenting the installation so that you confirm that everything's is operational and been set up and working properly, right? So there are checks in there. It tells you that you should be checking the heating, checking the cooling, the modes of operation, confirming your superheat subcooling, making sure your temperature differentials are within that posted in the manufacturer's submittal. It tells you in a heat pump operation, right, that your auxiliary heat or your secondary stage of heat is only working at the point at which your heat pump can no longer maintain the load, right? So that you're not using your auxiliary heat with your heat pump at all times. That would be energy inefficient. You want to use the heat pump first and then your auxiliary heat. It does discuss balancing of systems. We'll talk a little bit about that next. It specifies requirements for duct leakage testing. Most districts that I know of don't necessarily require duct leakage testing at this point in time. However, some are starting to adhere to this. This is more so a commercial procedure where you pressurize the duct, figure out how much air you're leaking out of that ductwork, and therefore you get a leakage rate. So it gives you the guidelines. And I think this is actually in alignment with the IECC. The guidelines basically are for existing systems. If you were to actually do a duct leakage test, you should be less than or equal, no more than 20% leakage rate. For new systems within a thermal envelope, no more than 10%. And if your ductwork is outside the thermal envelope, basically if you're in crawl space or an attic, it's no more than 6%. So back to the conversation we had earlier about sealing up ductwork. If you don't seal up your ductwork, you seal up all your connections, you'll never meet these requirements. All right, your ductwork can be very, very leaky if all connections are not sealed. So take the little bit of extra time to seal all your ductwork connections before insulating, and you'll make sure, and you won't have a problem with duct leakage. It also defines owner-operator education, specifying some guidelines as to training the customer, making sure that they have the O&M manuals, and making sure that they know their warranty, as well as also how to operate and maintain their systems. So in that last slide, we talked about balancing. It's often not times done in a residential setting. However, commercially, it's done all the time. This ensures that you've got the correct airflow to each of your rooms. So during your manual J, if you did a room by room analysis, you would have figured out how much airflow you need to condition that space. You, in theory, should actually measure. I know a lot of people don't do this, but and oftentimes it's not required, but you should actually be measuring how much airflow is going into that space to make sure that you are within tolerance of the airflow to that space, to make sure that space can be properly conditioned. There's a lot of leeway in houses. Doors are open. There's migration of temperature and everything like that, of air. So there's a lot of leniency, but in theory, each diffuser that you set should have the required amount of airflow based on your manual J calculation. There's a few methods of measuring the airflow. All right. So that bottom right is a bolometer. Sometimes it's referred to as a hood. It directly measures the amount of airflow coming out of a diffuser. Right, that's your primary method. You can do a traverse in ductwork, right? Basically, you take average of air velocity. Within that ductwork, there's charts to tell you what your distances should be and where you should take your measurements. To measure your airflow, that can be done on branches, and that can be done at the main trunk, or you could take a pressure differential across components. Manufacturers will often post pressure differentials for given airflows, across coils or units. You can use that and correlate that to the chart, figure out what your differential pressure is across across the equipment, and then correlate that to an airflow. It'll get you close. Best method is a traverse if you're trying to find airflow, or a direct measurement via hood. Same thing goes for water. Water balancing, probably any installation in a common boiler, nobody's doing water balancing, right? You turn your pumps on, maybe you got some temperature control or something like that, but that's about it. Nobody's actually verifying any water flows. On these newer systems, heat pump system with electric boiler backup and your different zones and different pumps, mixing valves, buffer tanks, everything like that, you'll need to measure flow to make sure that you're not blending water in the wrong direction. So, not necessarily a big common practice these days. Commercially, it's done all the time. Residentially, not so much, but this will likely be needed as the systems get more complicated. So, something to note. It can be done directly with a flow meter shown in the bottom left, or you can use manometer and probes, basically measuring pressure. The simple way is to use this picture on the right is a differential pressure meter for water. It measures differential pressure for you across either a component, or in this particular case, that's actually a balancing valve. So you'll measure differential pressure across that balancing valve. Balancing valve manufacturers have charts that correlate the pressure that you measure with the valve setting and tell you what the actual flow is based on that differential pressure measurement. And then that can be adjusted. So you can allow more flow or less flow depending on what the requirement is. Just some summary best practices, in summary, I should say. Follow your manufacturer's clearance requirements for instructions. Ensure adequate clearance for maximum snow depths. Make sure your refrigerant line sets are properly insulated, properly installed, covered. Make sure your penetrations are sealed. Make sure all your electrical conduits outside are watertight. For your indoor units, make sure you have the proper clearances. Any wall hung units, make sure you have the proper clearance above the unit itself. The manufacturer will tell you what the minimum clearances are. Make sure you seal all your envelope penetrations properly. Make sure you route your exposed line sets and wiring in line set hideaway. So if you have your line set and exterior walls, as shown in the bottom right, the line set hideaway is a good way to basically hide your line set, hide your condensate line, and hide your power line. So from the outdoor unit, these outdoor units typically power the indoor units. There's a wire that would go from the outdoor unit to the indoor unit, and that carries your power and communication wire. So everything gets put into a line set hideaway. You can route your line set hideaway. It comes in pieces. It's 2-piece. You can mount the bottom piece right to the wall, run it all the way to from end to end. Install your line set wire. You can run your drain down into this as well. You just have to penetrate on the bottom some, or at a low point. Once all that is set, everything's been done, everything's been started, you can put your top cover on. You can even paint it if need be. They make penetration fittings as well, as shown in the bottom here, that can get screwed and mounted directly to the wall, and then that can be sealed tight so that you don't have any water infiltration. Make sure to remove excess line set. There are some minimum requirements on these units as far as the minimum amount of line set, not just the maximum. Remove anything that's extra that you don't need. Just for cleanliness, make sure you're not trapping anything, trapping oil or anything like such as that. Make sure, again, I mentioned your line sets being insulated properly, end to end. If you got to make connections, tape, make sure you put tape around them, seal them tight, or glue, so that water can't infiltrate inside the insulation as well. On heat pumps, both sides need to be insulated. It's not always a liquid and a vapor line. Both serve as both switch roles, right? So cold and hot. depending on the mode of operation. And again, cold weather, climate, heat pump installations, make sure you are above the snow line, right? The snow design parameters in that area, and make sure you have enough space underneath for proper drainage so that you do have good operation and you're not, burying your units in snow. So that's pretty much that's the end of this session. If there's any questions, we can take them, at this time.
Great, thanks, Ken. We do have a couple questions. First one
Sure.
is, any suggestions about how to isolate sound from outdoor units that are mounted on a wall bracket?
How to isolate, what was that question again? How to isolate for, was that for
Isolate
vibration
sound.
or sound? So on the outdoor mini splits, you'd be surprised how much they do not transmit into the house. There are rubber pads that will come with the bracket itself that you would mount the unit on to eliminate and isolate some of the vibration, but there's not a whole lot of vibration. It's not like your typical large condensing unit that you might hear humming along on the outside. There's inverters on the compressors and the fans. They're not always at high speed. They're much more balanced. It's rare that you would be transmitting into the interior. But there are rubber isolators that you would use as on top of everything else.
Got it, thanks. Ken, what are the typical operating pressures for an R32 and R454B?
So I got to think about this. So you wouldn't have R32 in residential. I think for the most part it's R454B. I haven't worked with it directly yet. The operating pressures, I believe, are a little bit higher than 410A. I couldn't actually tell you the norms off the top of my head. I'd have to look it up. They're a little bit higher than 410A. So I think the low pressure side is on the order of like 200. The high side is like 450. But don't take my word. Don't take my word on that.
Is R54B more combustible?
There is all right. So there is a flammability rating on R54B. They don't consider it a combustible. I was actually watching a blurb on this from one of the manufacturer's websites just yesterday, actually, on the rating. So rating on flammability, they usually give it a 1, 2, and a 3. All right. So 410A is at the bottom of a 1. R54B is actually in between a 1 and a 2. So they say it's slightly flammable. It's not going to blow up in your face if that's what you're concerned about. So, I mean, unless unless you did not evacuate the system before you're operating on it, your risks are extremely low of actually lighting anything on fire with it.
Gotcha. Okay. It depends on the manufacturer whether or not you need that liquid line to be covered.
It does in an AC only system. A lot of times you would not insulate the liquid line. Though some manufacturers actually will tell you, or they will tell you if it's going to be in a very hot environment so that you don't actually pick up any heat, they will tell you to insulate it. Regardless of that, on a heat pump operation, you should have both sides insulated. So just to limit any kind of transfer of heat between your line set and the environment, and the fact that either line could be cold and either line could essentially condense in operation. So another thing to note, we didn't really talk about it too much, is that particularly on the mini split systems, what I think a lot of people don't realize is that the expansion valve is actually in the outdoor unit. So even though you have a liquid line and a suction line, and you have liquid on one side, suction on the other side, technically that liquid line going from the outdoor unit to the indoor unit is actually a mixed phase. It's not completely liquid and it's not warm. So it's already getting cold, leaving the unit and going to the into the interior unit, which is why they tell one of the reasons, there's a few reasons, but that's one of the main reasons why they tell you to insulate both line sets on a heat pump, particularly on mini split systems.
Got it. Okay. Last question I'm seeing is, are there special venting requirements for rooms, indoor heads that use R54B in case of leakage?
Not that I'm aware of, not at the moment.
Okay, great. Well, thank you, Ken. I appreciate your time creating these slides for this series. And obviously, if anyone has any additional follow-up questions, don't hesitate to reach out. And we hope to see you next week at our next Wednesday webinar.